Okay, we're going to start chapter number 9 today. Sinusoidal steady state analysis. Sinusoidal steady state analysis. The idea is that so far we have only been looking at DC sources, right? So far. We have only been looking at sources whose voltage or current is constant with respect to time. Okay, these are called DC sources. In this chapter, we're going to look at AC, or time varying signals. Let's see this guy. Specifically, we are interested in one wave, the sinusoidal wave. Okay, this guy. This is actually a cosine wave, right? So a time varying signal, it could be voltage or a current. How does my circuit respond when I apply a time varying input? Okay, and I'm going to look at cosine and a sine as a stand-in for all time varying repeating signals. Or in other words, if I can understand the behavior of circuit when the input is sinusoidal, I can extend my understanding to any time varying signal. So in other words, in engineering 117, in EEE 117, you'll see that any repeating wave with a regular time period can be expressed as sum of different sinusoids. Okay, the idea being, if you understand sinusoidal response, you can extend that understanding to other time varying repeating signals. Okay, so the bottom line is that sinusoidal analysis forms the basis for our understanding of how circuits behave. Okay, how do circuits behave when their input is not constant but varying with time? Okay, that's the idea of this chapter. So we are going to talk about time varying voltages and currents, time varying voltages and currents. And then, like I mentioned, sinusoidal source is one particularly useful source in the sense that if you understand the behavior of a circuit to a sinusoidal response, sinusoidal wave, then you understand, then you can extend your understanding. Okay, now to accomplish this time varying view, Phasor method. Okay, so the idea is this. Let me talk about this concept upfront. Okay, and it's not until later on that the flow of the chapter actually dictates that we talk about it. But in the interest of giving you some clarity upfront, what I'm going to do is to talk about the idea of phasors. Okay, the idea of phasors right now in a summary view before even we go on to talking about sinusoidal response. Okay, let me see if I can add a page here. Okay. Polar and rectangular form. Of complex numbers. All right. So the idea is any sinusoid can be expressed in the form of a phasor. Okay. So I'm going to represent using a Cartesian coordinates complex numbers. Let's say on the x-axis, let's say I have a complex number, 1 plus j1. Okay, 1 plus j1. You know how to represent a number 1 and 1. Okay, 1, 1 on a Cartesian plane. Okay, now if the x and y axis here, x-axis is the real axis, and then the y-axis is the imaginary component. So what I'm trying to do is to represent this imaginary, this complex number, which has a real part and an imaginary part. Okay, a complex number which has a real part and an imaginary part can be represented in a Cartesian coordinate, in a Cartesian plane, where x is the real axis and y is the imaginary axis. Okay, this is actually j, y, imaginary axis. Okay, so if I had another real number, so if I had another complex number, 3 plus 2j, okay, then I would go 3, 1, 2, 3, and then I do my number somewhere in here. Okay, that would be 3, comma 2, where 3 is the distance from the imaginary axis and 2 is the distance from the x-axis. So this guy represents 2 and this distance represents 3. So this represents the real part and then there's the imaginary part. Okay, so the idea is that any complex number with a real part and imaginary part can be represented on a Cartesian coordinate, on a Cartesian plane. Okay, now also in addition to that, okay, my argument is that in addition to representing it using a point in a Cartesian plane, the exact same, let's see, this guy, this fellow, okay, can also be represented using a straight line, okay, with a magnitude and an angle called phi. Okay, let me clarify that. Let me give you another example. Let's think of this number right here. Okay, let's think of a number right here. That's something like -1 and -1. Okay, that's in the third quadrant. So here is the first quadrant. To the left of this is the second quadrant. Bottom left is the third quadrant. And the bottom right is the fourth quadrant. Okay, now the number here, the point 1, -1, -1, I can show its location, I can specify its location using this x and y axis coordinates, -1 and -1. Okay, so the complex number corresponding to that would be -1 plus j -1. Okay, or I could do the exact same thing using this guy. Okay, using, I would say the distance from origin is square root of 1 squared plus 1 squared. It really is -1 squared plus -1 squared under root. That would be the distance. And there's an angle here, 45 degrees. Okay, there's a 45 angle here. Similarly, the exact same thing here, 1 squared plus 1 squared. That's the distance from origin to the point 1, 1, and an angle of 45 degrees. So the point I guess I'm trying to make is, given any point in the Cartesian plane, Take any point in the Cartesian plane. There are two ways to describe its position. Okay, one way is by its location, Cartesian coordinates location. Okay, 1, comma, -2, or the other way to represent this exact same number is through its distance from origin and the angle it makes with the x-axis. Okay, so these are two representations of the exact same underlying point. Okay, so one is complex number representation, which is shown as x plus j times y. Okay, or the other representation would be the phasor form. It's called a phasor. In this case, what I'm really doing is specifying the distance from this point back to origin along with an angle. Okay, so in other words, if your destination is to reach this point, let me put it in another way. Okay, if your destination is to reach that point 1 and 1, there are two equally valid ways that could get you there. Okay, one mechanism is to start at the origin, okay, and head east, due east for 1 mile, and then head due north for 1 mile. Okay, so that's one route you could take to reach that same point, or you could reach the exact same point by heading out northeast at 45 degrees for a distance of square root of 2 units. Okay, 1.414 miles. Okay, so the point I'm trying to make really is that these two are equivalent. You would end up at the exact same point. Okay, so now this is a very important concept for us to understand in this chapter, because it's very convenient to do sinusoidal math in polar and rectangular form. Okay, so the idea is simple. If you have sinusoidal waves, sine 30 plus phi, 30t plus phi, plus cosine 30t plus 2 phi, okay, something like that. If you end up having to add two sinusoidal inputs, okay, well, it's not pretty straightforward to do this kind of arithmetic in trigonometric form. So then what you tend to do is to convert these numbers into their corresponding real or imaginary complex numbers, and then do your arithmetic there. It's much easier to do your arithmetic, to do your additions in complex number form than in sinusoidal form, than in the trigonometric form. Okay, so I guess the bottom line is any sinusoidal wave that you're going to look at, and we're going to look at the formal definition for a sinusoidal wave. So any sinusoidal wave can be expressed as a complex number and as a phasor form. And depending on your convenience, you tend to represent them in any of one of these three forms. Okay, so let me also add that additional form here, a sinusoidal trigonometric form. So there are three representations that we are going to use, switch back and forth from, which is a complex number notation, and then there is a phasor notation, and both of these notations are actually representing the same underlying sinusoidal representation. Questions, please. Questions so far. And this becomes absolutely clear, hopefully, when we do enough problems. Okay? But that's a preview of what to expect. We're going to look at sinusoidal waves in their trigonometric representation, and then I'll show you how to represent that in a phasor form and how to represent that in a complex number form. Questions, please.
I have I have a kind of a random question, but
Okay.
I've noticed across different disciplines that the imaginary number gets represented by different variables. I've seen it used as I, and then I see that in engineering it's used as J. I just was wondering why.
I think it's just a matter of convention. I do not think there is any significance to the difference in choice between I and J. The only thing that really matters is MATLAB, for example, my understanding is that it prefers the variable I, but that both of them are representing the exact same physical quantity, square root of -1. Okay, but as to the particular reason as to why different notations are used, I would have to guess that it's just a matter of preference and notation choice across different software manufacturers.
Okay, I see.
Okay. But then you're right, the imaginary part is shown as negative, as shown as J, or as shown as J or I. Other questions, please. Okay, so let's move on, and then I'll come back to this topic over and over again. So this is just a preview, so don't be deterred if you don't get the gist of it, 100% of it. Yeah. Okay. All right, so let's look at the sinusoidal source, okay? In this class, we're going to look at the cosine as a representative wave, okay? We're going to look at the cosine as the representative wave. There are courses, there are textbooks that actually use sine as a representative for a sinusoidal source, but we like to use cosine as a representative wave. Okay, here now a sinusoidal voltage source produces a voltage that varies sinusoidally over time. Okay, let's say this is my cosine wave, right? Okay, now from what you know in your from your trigonometry, how is this different from a sine wave? How is this different from a sine wave?
It's shifted?
It's shifted, thank you. So the sine wave, that guy is a sine wave. So this is sine omega t, okay? And you notice that this sine wave is beginning at the origin, and then there is an amplitude Vm corresponding to that. So the bottom line is sinusoidal and cosine waves have the exact same structure, except that one may be a time shifted version of the other. Okay, phase shifted version of the other. Okay, so this is a repeating sinusoidal wave. So let me do this. For now, I'm going to park this to one side. Okay, I'm going to park this to one side. So now, let's see. Okay, right there. Now, this is a repeating wave. This part of the wave keeps repeating over and over and over again. So we can write the time period, the frequency at which it repeats, that to be t. Okay, and then 1 over t gives frequency, and 2 pi times f gives the angular frequency. Okay, angular frequency. Okay, now this is a cosine wave, not quite a cosine wave, but it seems to be a pure cosine wave. Okay, if there were, this term was not there, if this phi term was not there, would appear something like this. Okay, let me bring it over here. Let me try to zoom this out enough. Okay, let's see. Your pure cosine wave would look like so. Okay, the idea being it reaches its peak value. A pure cosine wave reaches its peak value when at time t equals to 0 or angle 0 degrees. Okay, if you remember, cosine of 0 is 1. That's the maximum value a cosine can see. Now, what you want to remember is, what you want to understand is this guy. Okay, cosine omega t is shown in here, the purple wave. Okay, now if I add some kind of phase to it, okay, by adding a phase to it, what I'm really doing is shifting this cosine wave in time. Okay, that is really what is happening because of this phase. Okay, now we have a very good understanding of all the components in this equation here. If you look at the equation there, okay, if you look at the equation there, there is a peak amplitude term Vm that represents the maximum value in any direction. Okay, so this is negative Vm, and the one on the positive side is a positive Vm. So we know about that. Okay, we know about Vm. Also, what is omega t? Omega represents the frequency, or how often this complete wave is repeating. So this is the frequency. Now, how about the phase? I just showed you that phase represents the shift, the time shift, or the shift along the y-axis. Okay, let me duplicate this. Okay, so the idea being a cosine wave with phase shift is only shifting left or right. Nothing else is changing. Its amplitude is not changing. Its frequency is not changing. The only thing that is changing really is its time offset. Where is it reaching its peak? At what time is it reaching its minimum? And at what time is it reaching its zero value? Okay, it's only laterally shifting. That represents a phase shift. Okay, so this guy here is a cosine wave, omega t plus 0 degrees. Okay, plus 0 degrees Vm. Okay, that represents the phase shift. Here, the phi angle phase is 0 degrees, and that's the reason why you see the cosine wave reaching its maximum at 0 times 0. Okay, so that's the idea. Questions, please. Questions so far. So here is a representation of a cosine wave, and we are capturing information about its frequency, about its maximum amplitude, and about its phase. And that's all the information I need. That's just about all the information I need to fully represent a cosine wave. Questions? Okay, so here is a cosine wave. Okay, the phase angle phi determines the value of the sinusoid at t equals to 0. Okay, so for example, if the phase angle is 90 degrees, I just mentioned that it represents, depending on the value of the phase, okay, depending on the value of the phase, if the phase is 0 or 100 or 90, this cosine wave shifts left and right, okay? It coincides for a value of phi. It's like this for a value of phi equals to 0. This is for a phi is 90, so on and so forth, okay? So phase angle really represents the value of the cosine wave at time t equals to 0. Okay, so for example, if phi is given to be 90 degrees and Vm is given to be 8 volts, okay, what it really says is at time t equals to 0, I'm going to plug in. So let's say this is my cosine wave, right? So I'm going to plug in a value of 0 for t, and I'm going to plug in a value of 90 for phi. Okay, so what is going to happen is that this term is going to cosine 0 plus cosine 90. So I'm going to end up with 8 cosine 90 degrees, which comes out to be 0, cosine 0. Cosine 90 is 0. All right, so if we are given the value of phi, we should be able to find the value of the cosine wave at time t equals to 0. Okay, and now we usually represent the phase angle in degrees. Phase angle is represented in degrees, but it can also be expressed in radians. Okay, so the relationship that you want to remember is in a full circle of 360 degrees, there is 2 pi radians. And from there, you can calculate how many radians in 45 degrees. Well, that's simply pi over 360 times 45. Okay, so the idea is the only relationship that you want to remember is that in full circle of 360 degrees, there's 2 pi radians. And you can go back and forth between radians and degrees. Okay, questions, please. Okay. So here is an example. Let's start by reading this given information. A sinusoidal current has a maximum amplitude. When I'm reading maximum amplitude, I'm automatically taking that value into the variable Vm. Okay, and the time period of the source is 1 millisecond. Okay, the magnitude of the current at t equals to 0, when t equals to 0, the magnitude of the current is 10 amperes. Okay, I is 10 amperes at t equals to 0. So we are asked to do a bunch of things. What is the frequency of the current? There's more than one question in here. So the first question is to find the frequency of the current. That's an easy part. Frequency of the current is really 1 over t, which is 1 over 1 millihertz, which is milliseconds, which is 1 kilohertz. And if you want to express that in omega, that's going to be 2 pi over t, or 2000 pi radians per second. So that's the easy part. Given the time period, you can find the frequency. You have been doing this from your high school. That's not the difficult part. Okay, how do you get the expression? The second question is what we are after. How do you find the expression for I of t? Okay, what is the time domain representation? What is the time domain representation for this guy? Well, the time domain representation I know has Vm or IM component. So excuse me for that. I should have taken this down as IM because this is current, right? Current maximum. So IM is given to be 20 amperes. Okay. Omega, I just found out omega to be 2000 pi. Okay. And T is the time, of course. And phi, I don't know phi. Okay. If I knew phi, okay, if I knew phi, then I would know just about everything in here. I know omega, I know IM, and it's this phi that I have to find out now. How can I do that? How can I find out phi? Well, I can find out phi from the information that is given for t equals to 0. Remember, let's go back. Okay, what is phi? The phase angle phi determines the value of the sinusoid at t equals to 0. So what has been done is the value of the sinusoid at t equals to 0 is given. You're asked to find phi. Okay, let's see. Let's see if we can do that. Okay, and for that we are going to make use of this piece of information. Okay, let me see how I can make use of that piece of information. I at t equals to 0 is given to be 10 amperes. But I know the value is going to be 20 cosine 2000 pi times t, which really is given to be 0 because we are evaluating at time t equals to 0, plus phi, all of that equals to 10 amperes. So cosine, all of this goes to 0 because that's all multiplied by 0. Cosine of phi has been given to be 10 amperes over 20, which is 1/2. So phi is really cosine inverse of 1/2, which is 60 degrees. Okay, so to recap, we have been asked to find the time domain representation for this guy, which is Im cosine omega t plus phi. We have been asked to find that representation. Well, in order to find that representation, different sources of information is given. We were given the value of Im as the peak value. We were given the value of omega in terms of the frequency or in terms of the time period, okay? And the value of phi was given in terms of I at t equals to 0. Okay, if you know the value of I at t equals to 0, you should be able to find out the value, the offset. Does that make sense?
Yes.
Okay, that's good. Okay, it's a very, very simple problem where given different pieces of information, we can express a sinusoidal wave. Okay, what else? Let's see. Now, so that's about the time domain representation of a sinusoid. Time domain representation of a sinusoid is using the trigonometric function cosine. Okay, and when it comes to sinusoidal waves, we cannot understand its average value because the positive and the negative half cycles dictate that the average value comes out to be 0. So in order to have a notion of some kind of average, we use what is known as VRMS instead, root mean squared. So all we're doing is first squaring the wave, okay, or squaring the signal, then integrating it or adding it, okay, over its entire period of interest or over one clock, one full cycle. Okay, by squaring, what I'm really doing is I'm converting the negative half cycles into positive half cycles. Okay, squaring, then adding, and then You take the mean of it over the time period, which is dividing by 1 over, and then you undo the square. Okay, so this kind of transforms your cosine wave and gives you some semblance of a mean. Okay, this is the closest you can get to mean in terms of a non-zero value. Okay, so this is something that we would do absolutely a bunch of different times. We do it often when we are dealing with statistical numbers that are evenly spread out across a mean of 0. If there are data points that are centered around a mean of 0, then a mean of 0 is, or the average value does not provide a whole lot of intuition to us. So in order to understand some semblance of mean, what we like to do is to square the wave. That's exactly what I'm doing here. Vm squared cos squared omega t. Then integrate it. What is integration? But for a continuous sum. So I'm adding the squares, okay? Then I have to, over the entire clock period, then I kind of average it by doing a division by 1 over t. And then I want to undo the square root, okay? And I really want to undo the square that I did before by doing the square root. This is called the root mean squared. The root mean squared. Okay, this is a very, very frequently used representation. Okay, a metric to understand, to gain some insights into your data, into your signals. Okay, root mean squared. When you do the trigonometric calculation for this guy, you'll see the VRMS of cosine wave or a sine wave is really Vm over square root of 2. Okay, so if I have a cosine wave, V of t equals to Vm cosine omega t plus phi. And I'm asked to find the VRMS for this guy, root mean square. That simply is V peak over square root of 2. Okay, that's all there is to the idea of a VRMS. Okay, VRMS is simply V peak over square root of 2. Okay, and that follows from a simple trigonometric analysis. Okay, now
Professor,
this,
can I ask a question?
yes, ma'am.
Would you say that that's why alternating current is more efficient at delivering power because it stays closer to 0? So it like delivers power to the resistor, but it's like, I don't know. Does that make sense?
That's one of the reasons. That's one of the reasons. Sure, but there are other reasons as well. For the choice between the DC and the AC, for household supplies, for household and industrial supplies. But that's a good point. That's a valid argument. Okay. Now this factor of 1 over square root of 2, this result is only valid for sinusoidal signals. Okay, when you evaluate the VRMS of some other kind of wave, that may not be 1 over square root of 2. So whenever you have sine or cosine waves and you try to get the root mean squared value of it, it always evaluates to VRMS over root 2. Okay. And now we also want to repeat the VRMS value when there is an offset, okay, DC offset. Let me explain what I mean by DC offset. Let's say I have a sine wave, a regular sine wave that goes up and down like this. This is a sine wave. If it is shifted by 90 degrees, that will be a cosine wave. Okay, so If I'm shifting it laterally, okay, along the time axis, that corresponds to a change, an increase or decrease in phi. That's the phase angle, right? So where is it along the time axis? Okay, if it is moving left or right, it represents phi. Okay, but if it is moving up or down, it's really represented by the DC offset. Okay, so for example, if I were to take this sine wave, okay, and then superimpose it at 5 volts on a DC value, okay, if I add some DC bias to it, okay, so this guy is 0, this guy is, I don't know, 5 volts DC offset. Okay, that's called the DC offset, 5 volts, meaning that the wave is shifted up or down. Okay, so this guy is going up and down from 5 volts. Okay, so that's the idea of DC offset. Any longitudinal shift up or down represents a DC offset. Okay, now if a sine wave has a DC offset, what would be its VRMS value? So I know the VRMS for this guy, right? VRMS for this guy is, if this guy is V peak or VM, the VRMS for this guy would be Vm over square root of 2. Okay, I know that from the foregoing analysis. But what would be the VRMS for a sinusoidal wave that's not at 0 volts DC, but it's at a DC offset value? How about the VRMS for this guy? Okay, if you want to find the VRMS for this guy, you do the simple trigonometric calculation again and see that it is VDC squared plus VRMS squared. So VRMS equals to square root of VDC squared plus VM squared over root. Okay, so think about it. If this DC value was 0, if this DC value was 0, then you'd get back your square root of Vm squared over 2, which is really Vm over square root of 2, which is your VRMS squared, VRMS at DC value equals to 0. Okay, so the DC value adds an additional term to the RMS, the root mean squared value of a cosine wave. Okay, so the VRMS for this guy would be, so in this case, VRMS would be square root of VDC squared plus Vm squared over 2. Okay, these represent the exact same wave, except that one is shifted up and the other is shifted down. Other is at origin. Okay, that's the idea of VRMS. What else? So here is the representation of the sinusoidal wave. So the first section of this chapter was all about representing sinusoids. We are going to use cosine as a representative sinusoid here. We looked at its frequency, its amplitude, which is Vm, the maximum value. Okay, frequency is omega or f, and then we also looked at its phase, which is phi. Okay, once we have these three quantities, we can completely characterize. Okay, we can completely characterize a sinusoidal wave. Three quantities of interest to me are its frequency, amplitude, and phase. Once we have these three pieces of information, we have a complete understanding of a sine wave, of a sinusoid wave. Questions, please. Now, the next idea that we are going to look at is what happens when I apply the sinusoid wave. So far, we looked at V of t is Vm cosine omega t plus phi. I saw that my voltage could be a sinusoid, or my current I of t could be Im cosine omega t plus phi. Let me call this as phi b. I'll call this as phi c to represent the difference as voltage and current. So the current signal could be varying with time as a sinusoid, or the voltage signal could be varying with time as a sinusoid. Now the question really is, if I am applying these voltages and these currents as inputs to my circuit, how is the circuit going to behave? That's the idea of this chapter. That's the idea of this section, sinusoidal response. How does a circuit respond when the input is a sinusoid? Okay. So there are two parts to a response. Okay. There is a transient response and a steady state response. So whenever there is a circuit and I apply an input, the output of a circuit that gets an input can be divided into a transient output, which is a knee-jerk short-term output, and then a steady state output. Okay, it's a steady state output as well. This is the response that the system settles into. So the bottom line is the overall response.
Meaning we're first. We're lower than the world. They're faking their statistics. South Korea be investigated. Have you been watching television? We've arrested a lot of people. Obama.
Okay. The overall response is the sum of the transient output and the steady state output. Okay. The transient is the knee-jerk sudden output that occurs when the input switch is just turned on. Okay, so when we input any signal into a circuit, we expect to see an initial response that's called the transient response. Okay, and then after a long time, after we have given it enough time to settle, we see a response that persists forever. Okay, that's called the steady state response. Okay, it's called the steady state response. In a very crude term, if I were to give you a very crude example, let's say you are beginning, you're in a car, you're trying to, okay, that's my artistic representation of a Tesla car. Okay, let's say you're trying to begin driving towards your destination, and then you accelerate. What happens is the way your body responds to this change from zero velocity. Okay, zero velocity is that you're going to swing backwards when you accelerate, and then after you continue to drive for some time, that initial response of pushback, okay, is going to subside, and then you're going to carry on with a constant velocity or constant acceleration, as the case may be dictated by the driver. But the idea is the way your body responds inertially when you're sitting back or when you're taking off in an airplane, for example, is that there is an initial time, there is an initial temporary transient response, okay, initial response that you accelerate a bit of a pushback, that you experience a bit of a pushback, and then you eventually settle into a constant velocity. So that's more or less a crude representation. That's a crude representation of what is happening when the inputs or when the circuits are subjected to sinusoid inputs. Okay, when the inputs are subjected to sinusoid inputs, they experience an initial knee-jerk reaction that is akin to you experiencing an acceleration when your flight is taking off. And then after some time, when you reach a cruising altitude, when the flight reaches a cruising altitude, you settle into a steady state response. So that's exactly the idea here. There is a transient response, an initial knee-jerk reaction, and then a final steady state output. Okay, so in this class, we'll only be looking at the steady state output. Okay, we'll only be looking at the steady state output. Okay, and then there are certain characteristics, certain properties that are applicable for sinusoidal input when we have a linear circuit. When we have a linear circuit, okay, so the steady state response of the circuit is also a sinusoid function. So in other words, I'll give you an example. Let's say I have a resistance, okay, and I apply a sinusoid voltage as input, okay, voltage, sinusoidal voltage as input. The output, the response of this guy is also going to be a sinusoidal function, okay. The output, if you were to look at the voltage dropped in this guy, okay, that's going to be sinusoid as well. So in other words, the response of a circuit is also going to be sinusoid. Also, the frequency of the input and the frequency of the output are exactly the same. So if you were to look at the frequency of this sine wave and the frequency of this sine wave here, they are going to be exactly the same. Okay, the frequency, linear circuits do not change the frequency. Okay, do not change the frequency of the input signal. Well, what changes though is the amplitude. Okay, let's say that's your input. Okay, the output is going to be the same frequency, the exact same frequency. However, okay, the amplitude could be different. Not only the amplitude, the phase could also be different. Okay, in other words, this could be time shifted left and right. The output could be, with respect to the input, time shifted left and right. Okay, when the input and output are exactly reaching their peak and bottom at the same time, like so. Okay, in this case, both the input and output are reaching their peak at the same time, maximum. Similarly, they're reaching their minimum values at the same time. So we say the input and output are in phase, but then they could be different. Okay, for example, in this case, the output is reaching its maximum positive when the input is at its corresponding minimum. So they're out of phase by 180 degrees, so on and so forth. So the bottom line is, in linear circuits, okay, the input shown in red and the output shown in blue have the exact same frequency. See, one full wave takes the exact same time, both for the blue wave and the red wave. That's a fundamental principle of linear circuits, that the output frequency is exactly same as the input frequency. However, what could be different is the amplitude. The amplitude could be different. Okay, the amplitude could be different. Okay, and then of course there could be different peaks, different offsets. Okay, the input and output could be offset in time, and the input and output could be offset in amplitude, but not frequency. Okay, therefore the frequency of the input signal is the same as the frequency of the response. When I say response, I mean output. Okay, when I say response, I mean the output. Okay, the amplitude of the response depends on the circuit. The amplitude of the output could be different than the amplitude of the input. Okay, it most likely will not be the same amplitude as the input signal, but that's all right. Okay, the next thing, like I mentioned, is that the phase of the circuit's output will be different from the, could be different from the phase of the input. That's exactly, all of that information is shown here. Okay, they're different phase because they're offset in time. They're different amplitude because they have different values for maximum and minimum, but then their frequency is still the same. Okay, so that's the behavior of a linear response, linear circuit. Input, output of linear circuit. Questions, please.
How will we know if our circuit is linear?
Yeah, in our analysis, in our codes, we always look at linear circuits. Okay, but the definition of linear circuit is this guy. Okay, the idea of linear circuit is a function of x plus delta y, delta x is going to be function of x plus function of delta x. So this would be the idea of linear circuit. Sinusoidal superposition principle applies. We know the circuit is linear if superposition applies. Okay, so if you can, let's say y equals to mx plus c. Okay, y equals to mx plus c. This is a linear circuit because I'm not going to do the exercise, but I welcome you to do that. If you were to change, if you were to apply the value of x, okay, and find a value of y, and you apply a value of x plus delta x and find the value of y, let's call it y prime, y double prime, okay, then you'll see that y double prime is really y prime plus delta y, where delta y is function of this change. So the idea is if superposition holds good, you know that your circuit is linear. And most oftentimes in this class, we are only dealing with linear circuits. Okay, so that's the idea. And then did that answer your question at all?
Yes.
Okay. Now, so for example, I'll give you another example. This guy is not linear. Y equals to, I'll give you an example of y equals to x squared. Okay, so on the other hand, this guy is linear. Y is x, is linear. Because if you were to change, if you were to pick a value of x to be 2, okay, x1 to be 2, what's the value of y? 4, okay? How about here? Okay, if I pick a value of x1 to be 2, the value of y1 is 2. Okay, now try increasing the value of x to by 2 plus 1. Okay, what would be y2? Try increasing the value of x by the same amount, 2 plus 1. What would be y2? Y2 would be y1 plus function of delta x. Okay, so here delta x is the change in x is 1. So y1 plus function of delta x, which is simply y, right? Delta x, f of x is y, right? X. So this is 1. Okay, so this is delta x, which is y of 1. So this is delta x. In this case, it's going to be delta x. Okay, which is, so the idea is if you were to increase x by a small amount, y is going to increase by a corresponding amount. But then in nonlinear circuits, y changes not by the same amount, but by a nonlinear amount. Y equals to 9. Okay, so you see that delta y squared is not equals to x squared plus delta x squared. Okay, if this were true, that would be your linear, but that's not the case. There is an additional 2 delta x times x term over here. So this is what makes it non-linear. Okay, so that's the idea. So sorry about the long explanation here. I'm not going off tangent, but I'm spending a whole lot more time than I intended to on the idea of linear circuit. Okay, but that's all right. That's all right. So sorry about that. So in this class, you can pretty much assume that the circuits that we are going to see are all linear circuits. Okay, they're all linear circuits. If the input-output relationship is a straight line, then you know that it's a linear circuit. Okay, questions, please. Other questions? Okay. So let me go back and annotate. So this is f of x is x squared. Okay. F of delta x is delta x squared. So the formal definition is this guy. If f of x plus delta x is f of x plus f of delta x, that would be a linear circuit. If this is not the case, then we have a non-linear circuits in our hand. Okay. All right. That defines a linear circuit. Questions, please. Questions so far? Okay. Sinusoidal wave. So we looked at a sinusoid so far. I mentioned that both the voltages and the currents could be represented using sinusoids. And in this class, we are going to use cosine as our favorite sinusoid. And I kind of gave you a preview as to why we use a phasor. Okay, phasor is nothing but an alternative representation. Phasor is an alternative representation of a sinusoid. Okay, it's important that we realize this because we'll be doing conversions left and right, back and forth from one representation to another representation without obviously realizing that they represent the exact same thing. Okay, I already talked about phasor. Okay, I already did talk about phasor. Okay, we'll go back to that slide and then review what is necessary. Okay, and it's all based on the Euler's identity that e to the j theta is cos theta plus j sine theta. Okay, e to the j theta is cos theta plus j sine theta. A e to the j theta is a cos theta plus a sine, j a sine theta. Okay, we'll talk about that. We'll show that. Okay, now if you have, so let me show you the most important part. Okay, let's say if you have a sine wave, a cosine wave. Okay, let's say we have a cosine wave that looks like this, a sinusoid. Okay, then Vm and the phase angle, these two together represent the phasor of the sinusoid wave here. Okay, so if you have a sinusoid shown in the time domain, okay, then you can simply grab its maximum value, okay, and also its phase angle and call this representation the phasor. Does that make sense?
Yes.
Okay, let's go back to my earlier slide and see what I can, how I can relate them here. Okay, let me see if I can go all the way back to this slide. Let's copy this, okay, and then come back to this slide over here, okay, and add a page somewhere here, okay. Let me add a page here. Let's see, paste, okay, okay, there you go. Delete page, okay, so here, okay, I mentioned earlier that the trigonometric representation, okay, the trigonometric representation, okay, which is Vm cosine omega t plus phi, okay, can be represented using this guy. So in this case, A is Vm, okay. So in other words, I can grab this, I can translate this time domain representation into its phasor domain, okay, by simply selecting this guy, okay. The amplitude represents this term over here, okay, and the phase from the time domain represents the phase angle here, okay. So there is an equivalence. You see what I'm saying?
Yes.
How can we relate that? So let me clear this up a little bit, just so we can analyze this a little bit more, okay. So I'm going to clean up all of this. So while I'm doing that, I want you to think about how we can explain their equivalence in terms of the circuit diagram here. Okay, I mentioned that this guy, okay, is equivalent to this guy. Okay. So this sinusoidal representation, this is the time domain representation, is exactly equivalent to the phasor representation. And I want you to think about why that is the case.
So the amplitude or the voltage could be, so it's represented by the magnitude of the vector.
It's represented by the magnitude of the vector, which is this guy. Yes,
Okay, okay.
correct. What else? So if you think about it, I'm going to make a leap here, not quite a leap, but I'm going to show something that ties the three concepts together: the complex number representation, the phasor representation, and the trigonometric representation. Let's see. Okay, let's see what we can do here. I'm going to clean this up further. Okay, let's try to evaluate the distance, okay, from this point to the x-axis. Okay, what would that value be? Is it fair if I set this value is so again, Vm in this case equals to A. So I'm going to use them interchangeably. So don't be confused by that. Okay. So if I take a number 1.1 in the Cartesian plane and call this guy to be Vm or A, let me say A cos phi, would you have any problem?
Nope.
How about this guy? How about the distance between this point to the x-axis? What would that value be?
A sine phi.
A sine phi. Thank you. Because remember, if this is your phi, okay, the opposite side to phi is A sine phi. The adjacent side to phi is A cos phi. Okay, so now if you want to represent this number, so it turns out that this guy, A sine phi, is the x coordinate, okay, or A and A cos phi is the real part. So if you were to represent this number, A cos phi, comma, A sine phi, because it's a distance from the y-axis, which is the x coordinate is this guy, the y coordinate, okay, its distance from the x-axis is the, so if you were to represent it in complex number form, let's see if you can help me with this. What would its representation be in complex number form?
This would be A cosine phi plus J A sine phi.
Thank you. Thank you. So here are three different representations of the exact same underlying sine wave. Okay, you think about it. So now the phasor transform, so there is a union, there's a marriage between the three. Okay, when I represent it in complex number format with the value of A, with the value of x and y given, with the value of x and y given, I should be able to translate that into the phasor domain and I should also be able to translate that into the time domain. Okay, we'll talk about that shortly again. Okay, but the idea is, if you have a time domain wave, Vm cosine omega t plus phi, and you're asked to do the phasor representation of it, all you have to simply do is Vm angle phi represents the phasor for the time domain. It's called the phasor transform. Does that make sense?
Can I ask a question?
Yes, yes, ma'am. Go ahead.
If this was Vm sine of omega t plus phi, then would the phasor also be the same?
The phasor, that's a good question. What you'd have to do is you have to convert sine wave, okay, into cosine wave by adding a 90 degrees or by subtracting a 90 degrees. So the idea is you want to express all of that in cosine wave. So depending on that, if your input is a sine wave, you'd actually see that the phase angle changes by 90 degrees.
Okay.
We're going to look at an example for that. Does that answer your question?
Yes, thank you.
Yep. So if this were a sine wave, then you'd have to change the phase angle. Okay, 90 minus 5, 5 minus 90, depending on the exact value. Other questions, please. Okay. Now, let's see, the next topic we're going to look at is the idea that how passive circuit elements behave in frequency domain. Okay, how does a resistor, how does a capacitor, how does an inductor, R, L, C, behave in frequency domain? Okay, that's the idea. Okay, that's the idea that we want to understand. Okay, let's see. Now, if this were a sine wave, you would apply the, if this were a sine 90 minus theta is cos theta. Okay, so you'd apply this trigonometric relationship, convert this sine wave into a cosine wave, and take that corresponding angle for your phase angle. Okay, corresponding to that, you'd get your phase angle to be 90 minus 5. Okay, all right, so let's see. The next topic is how does RCL, how does each of these components behave in frequency domain? Okay, I'll give you a spoiler alert again. I'll give you a summary. Why don't I write this summary of this just so it's easy for you, summary. V, voltage of a resistance, is I of a resistance times the resistor. Okay, Ohm's law still applies in frequency domain. Okay, how about V of an inductor? You remember the expression for the V of an inductor in time domain? L di by dt, right? This was the expression for voltage across an inductor in the time domain. If you convert it into frequency domain, and I'll show you how that is done, for now, just trust me on this, you'll get what is known as ZL impedance, ZL times L. Okay, so similar to L, R, there is a ZL term. So let's look at VC in the frequency domain. You know, I is C dV by dt, okay? And then V would be 1 over C integral of I, okay? In the time domain. In the frequency domain, VC equals to C times ZC, okay? Or did I say it wrong? IL. Sorry about that. So it's IL. Okay, so you'll see that in frequency domain, you don't have to worry about doing the differential equation. You don't have to worry about doing the L di by dt. All you have to do is to apply a modified version of your Ohm's law. Okay, so your modified version of your Ohm's law. If you look at this circuit, if you look at this part, okay, it appears like this is I times R, except that this R is actually complex resistance or complex impedance, okay, where ZL, ZC, and R represent impedance, okay. They're not purely real numbers, they're complex numbers, okay. Complex resistance is called impedance in some sense, okay. So you see that Ohm's law plays out in frequency domain in this fashion, okay. And then we're going to see how that equation comes out to be, okay. So in summary, what we have is that a resistance in the time domain, IR is the expression, time domain. In the frequency domain, this does not change. It still behaves like I times R, okay? In the time domain, an inductor, okay, L, V is L di by dt in the time domain, right? However, in the frequency domain, V of an inductor is given by I times ZL, okay? Similarly, a capacitance in the time domain is I C dV by dt. In the frequency domain, the voltage across a capacitance VC is IC times ZC, okay? IC times ZC. So there's a parallel to Ohm's law in each of these circuit components corresponding to the frequency domain. Does that make sense? Now, if it comes down to finding the value of ZL and finding the value for ZC, if we know that, we should be able to find the value for V. Okay, so here is a summary. Now, before we get lost in a corn maze of equations and simplifications, I want you to have a clear head and understand that this is where we are headed through this analysis, just so you know what to expect and you don't lose sight of your target. Okay? So this is exactly what is going to happen now. You take the V is IR relationship, okay? And then for the resistance, you apply this V equals to IR relationship, okay? So V is your time varying voltage, R is your constant resistance, I is the current. So what happens, what's the voltage? The question really is, what's the voltage across a resistance if a current That's a sinusoidal current is applied. Okay, if a sinusoidal current is applied to a resistance, what would be its voltage? Okay, now you do the voltage analysis and you'll find out that V, voltage across a resistance, is R times I. Okay, that's the idea of R times I. You apply it and then you see that it comes out to be IR. Similarly, what happens when I take an inductor? Okay, when I have an inductor and apply a current I of t, that's not constant, but it is time varying. Im cos omega t plus theta I. If this current is applied or passed through the inductor L, what would be its voltage? Okay, that's the idea I'm trying to solve. In order to solve that, what we will do is to notice or start by what we already know. The voltage across an inductor is L di by dt. Okay, I do that trigonometric derivative of cosine is negative sine, and then because of the chain rule there is an extra omega. Okay, so when you follow through in this calculation, L di by dt, so we know inductance V is L di by dt, and when you plug in the cosine wave in place of I, you will end up with a relationship that looks like this. Okay, so voltage across an inductance is J omega L times I m e to the j theta I. Okay, so the idea is this is the current, that's the current I, and this guy, okay, this guy, we like to call this guy, we like to call this guy as Z. Okay, this guy is ZL. Okay, if you call this term as ZL, and if this guy is I, then your V is really ZL times I. Okay, your V is ZL times I. So when you have an equation that looks like this, J omega L times I, this guy is called ZL, this guy is your I. Okay, so we'll come back to talk about this. Don't worry too much if you don't understand this a whole lot right now. All you want to understand, all you want to remember is, so let me restate this. In frequency domain, okay, in frequency domain, the impedance or the voltage across an inductance is given by J omega L times Im e to the j theta I. Okay, e to the j theta I is your I, the applied current, right? So what happens to the voltage? What's the voltage of an inductor when you apply a sinusoidal current? Okay, that's the idea. The voltage across an inductance, okay, is J omega L. So this represents ZL times the applied current. Okay, if you remember, the voltage across a resistance is I times R. Okay, the corresponding term here is ZL and nothing else changes. So this is a manifestation really of Ohm's law. Okay, how did I get this? I simply got this by plugging in V is L di by dt, and in place of I plug in the cosine wave. Okay. All right. So let's look at the behavior of capacitance. Let's look at the capacitance in frequency domain. Capacitance in frequency domain. Okay. Capacitance in frequency domain, I is C dV by dt is the governing equation for a capacitor, right? I is C dV by dt. So if this guy, if V were given to be a sinusoid wave, what would be the current? If V input is given to a capacitance, you're asked to find I in a capacitance, a capacitor of value C, capacitance C. Okay, all you have to do is plug in Vm cos omega t theta V in place of little v, do the derivative. Okay, once you do the derivative, you're left with negative omega c Vm cos omega t plus theta V minus 90 degrees. You do a little bit of rearranging. What you will see is you can express this relationship between the voltage in a capacitance and the current in a capacitance to be this guy, 1 over j omega c. Okay, in this case, this guy, 1 over j omega c, is called as zc. Okay, you call that as zc and ic. So in other words, the voltage across a capacitance is given by the current multiplied by Zc, where Zc is 1 over j omega c. Let me go back. Okay, let me go back to the summary page that I started off with right here. Okay, I mentioned, and now you should see why that is the case, that VL is IL times ZL, where ZL is given to be J omega L. Similarly, ZC will be 1 over J omega C. Okay, so ZL is called the impedance of the inductance. ZC is called the impedance of the capacitor. And these are parallels to the resistor in the frequency domain. Does that make sense?
Yep, looks good.
Cool. Questions, please. Questions so far?
I
Okay.
think
So,
it's kind of hard to see what you're doing, but you're basically using the current as like a guess, sort of, for the derivative, and then
current,
you're associating the coefficients once you substitute it in.
yes, yes. So what I have done, I have not clearly spent a whole lot of time on this. This is the Phasor representation of it, and then go back and forth between Phasor and time domain. So I intentionally left a lot of gap in terms of the calculation here, because that's going to become much more apparent when we do the math example problems. For me, you're just going to have to trust me in the sense that the math is correct here. All I have done is, in place of C dV by dt, that's the fundamental equation I started off with. Okay, in place of V, I plugged in cosine wave and then did a bunch of math and then eventually arrived at the result that I want to arrive. Okay.
Okay.
So it's a little bit of a leap that I'm taking here back and forth, but hopefully that becomes clearer when we do enough math problems. Other questions, please. I know it's not, there's not broad daylight between where we ended up and where we started. Okay, and then we'll try to take it one step at a time. eventually. But I welcome you to go through this analysis here. Okay, it's simply based on the Euler's expansion formula. E to the j theta is cos theta plus j sine theta. Okay, so I welcome you to read through this analysis and see if you can make an effort to understand this before the next class, where we'll do some math problems and it becomes. Okay, we'll stop here.